So first, I'd like to welcome all the children on here who've come to find out a bit more. So the Angel School, we're the ones who will be hosting this course, and reason being is because we want to expose children worldwide to this incredible topic. So we've managed to have this education devised in a format that works for children as young as 9, which makes it one of the first of this type of course in the world. So we're very pleased about that. If you have any questions today, you're more than welcome to unmute yourselves and ask a question. Or if you're feeling a bit shy, you can type in the chat at the bottom of your screen, and we'll try and have all your questions answered. I'm going to tell you a bit first about the tutor, Eamonn Darcy. So he has a master's degree in e-commerce from Murdoch University and gained the Student Achievement Prize as the student with the highest academic performance of the graduating year. He successfully completed 4 university certificates on quantum physics, which you will also learn a bit about, quantum computing, including at the University of St. Petersburg in Russia. So very impressive. He owns a company called QEQA, which stands for the Quantum Education Centre of West Australia. And this is to spread the quantum word, especially to young people. So he's perfect for us here at the Angel School.
Oh, thank you.
And already, Eamonn has written 3 courses for young people. So the Magic of Quantum Computing for 9 to 15-year-olds, which is this one. Also, the Magic of Quantum Physics and the Magic of Quantum Consciousness. So those courses will also follow after this one for anybody who'd like to continue to learn a bit more, because some of them are so interesting, including quantum teleportation, which is a bit mind-blowing if you ask me. So Eamonn's going to give you a whole rundown about the course now and what you will learn and how interesting it is. And like I said, feel free to ask any questions.
Okay, can I take over?
Over to you, Eamonn.
Right, well, first of all, thank you very much for those kind words. I hope and trust that everybody can hear me okay. Natalie's totally right when she says how interesting this subject is, because it is exceptionally interesting. Quantum physics, children get it. I've had a lot of people say to me, oh, you can't teach 9-year-olds about superpositioning and quantum entanglement. And I always say the same thing to them. I live on a golf course and we have a club up here, and I'm always shouting my mouth off at the club. And I normally get a few people around me listening. And I can tell you now that it's the 9-year-olds and 10-year-olds and 15-year-olds who can follow me. It's the adults who can't follow what's going on. So, yeah, it's so unbelievable what happens in physics. And what's even more unbelievable is that we can harness these powers to actually make computations that we thought would never, ever, ever happen. These are amazing computations. The one I always refer to is if we use an ATM, the fastest computer on earth could hack into your transaction and get the PIN number, but it would literally take that fastest computer on earth literally 3 or 4,000 million years. So you're completely safe. A quantum computer could hack into every ATM transaction on earth in around about 6 seconds. So we're starting to simulate things like the Big Bang, simulate organic tissue. I've already done 2 presentations with an expert from Belgium on quantum genome sequencing. And that's very, very important because it's going to allow us to do customized medicine. So vaccines are something we talk about all the time at the moment because of COVID. But the reality is, with every single vaccine, it is very much a little bit of trial and error, because our fastest computers on Earth, digital computers on Earth, cannot simulate it. The exchange of electrons, they can't simulate it for more than a couple of minutes. It's like asking, what did you think of the movie? And the person only saw the first 30 seconds. Let me start now. And I do want to start off by thanking the very beautiful and very wonderful Natalie Bourne-Moses. Natalie and I have worked very hard on this, getting this to this stage. And Natalie is absolutely devoted to getting quantum physics and quantum knowledge out there in the market, especially to young people. So I'd like to thank her very much indeed. Okay, like Natalie alluded to, I've written 3 courses all this year. They're brand up to date. If you do these courses, you will know more than 99% of people on quantum computing, and you'll know an awful lot more than people actually in the market. I have not dumbed it down. I've explained it in a way that I think is, pretty pictures and telling stories, but the content is very extensive. It's a challenging course, and I say that with no other reason than it's true. So you have to accept the challenge, but trust me, it'll be really, really worth it. You'll find soon that you'll start just reading everything on this stuff because it is that interesting. I mean, look at quantum teleportation. As Natalie quite rightly said, quantum teleportation, it's unbelievable. Imagine putting a speck of dust on your palm of your hand, and then you just go boom, and then that speck of dust is 150,000 kilometers away. Now, and this has been done. This has been done many, many times now. I'm not saying it's been faxed. I'm not saying it's been photocopied. It's not been disassembled and reassembled. That actual particle of matter that existed here a millisecond ago is now 150,000 kilometers away. And you may well ask, how does that happen? But quantum teleportation is absolutely out of this world. Okay. So, now my aim is not to convince you that this stuff is important, because it's so obviously the most important thing, I think, and the majority of people in the IT industry and in every industry thinks this is the biggest change mankind will ever undergo as a species. And I say that seriously. You just look at the IBM, Google, Microsoft, Amazon, Alibaba, NASA. Everybody is all over it. Every government on Earth is spending billions of dollars in this technology. China's way ahead at the moment, followed by the US and Europe. UK is doing extremely well. And I must say Australia is doing well as well, which is very comforting. Okay, I'm going to take you through the course in 2 ways. What are the methods that we use to get the points over in an engaging way? And then the course content. And I think you'll be amazed with both. I might add that I can provide, what I like to do with the young people is get them to present to their family, their close friends, especially to the grandparents. I've got 3 grandchildren, one of whom I'm forever getting her to present to me. When she learns something new, I say put it on a presentation. So all of the presentation formats are given to Natalie at the Angel School, and she will give you a copy of the presentation that you can use as often as you like. And then I go over the course content, and you'll be amazed. We cover an awful lot, seriously. So the educational methods. One thing we say at the beginning of the course is that if you can, and I know sometimes you can't, but if you can, please get a mentor to do the course with you. And Natalie allows if you paid for one course, she allows another person to join in free of charge so that you can have a mentor, because it's so important. I mean, I know I'm probably preaching to the converted, but in all of my exams, my university career and everything, I have always deliberately gone and got a mentor, which is normally a fellow student. It doesn't have to be someone who knows more than you. It's someone that you can share things with. So throughout the course, I put in these cards, and they can talk about important points, exercises, games, discussions. And important points is so important because normally the mentor will be older. I suggest getting your grandparents, as long as they're slightly interested in your life, and let's hope that they are. They can see when I put in a card, I'm saying, hey, this is important. So the older, whereas the young student might let it go by, the mentor will say, now, make sure that the student gets this. For example, one of the ones, I can't remember where in the course this is, things the size of an atom or bigger behave the way we expect them to behave, and we understand them very well. And that's classical physics. That means that if I get a ball and I throw it, if we know the energy that I exert, the circumference of the ball, the resistance of the air pressure or vacuum or wherever I'm throwing it, we can work out exactly where it will land. That's how we landed on the moon. And it's, thank you, Vic, it is, we landed on the moon. At the end of every century, we always say, it's a bit of a joke in the physics science world, is that we say we now know everything. And you know something? As regards the classical world, we pretty much do know everything now. It's amazing. We know the 4 fundamental forces that exist in the universe: electromagnetism, gravity, the strong nuclear, which keeps atoms together, gluons, and the weak nuclear, which is radiation. We know all of these. We know it very well. We've had experiments tried and tested. And 100 years ago, we thought, oh my God, we know everything now. I mean, we have to brush up on a few things, but in general, we know everything. Quantum physics came along as if to tease us. And when scientists first developed the technology to look inside an atom, they were absolutely amazed at what happened. Because quantum merely means distinct, or it's a subatomic. Anything smaller than an atom is what is quantum physics, comes under the laws of quantum physics, and they're weird. It's absolutely strange. When scientists, and I'm including Einstein, Dirac, Bohr, Schrödinger, all these exceptionally clever scientists could not figure out, and we still haven't, how come the quantum particles, the subatomic particles, act so weird compared to when they all group together to become an atom. Because we know how an atom works. But an atom, now you are a quantum object. You're made out of atoms, sure, but fundamentally beneath those atoms are quantum particles, so you're made out of quantum particles. There is no doubt that nature reflects quantum physics not classical physics. There's no question about that. Quantum particles had to come first, and they did. And it's a totally different universe. The atoms and all of that are what we call emergent properties. They have emerged through interactions. But fundamentally, this universe, nature, the wonderful brain of the human, the wonderful nature that we see around us, is fundamentally quantum. And they do weird things, like they can communicate over billions of miles and act in sync with each other. So you can get one subatomic particle a million times smaller than a speck of dust. You could have one on the moon and one here. You change the one here, you change the spin of the one on the Earth, and the one on the moon immediately, at exactly the same time, changes. Now, you tell me, how does the one on the moon know that the one on Earth has just changed? Unbelievable. And Einstein famously called it spooky action at a distance. There's also a thing called superposition, whereby, I don't want to go into this too deeply at the moment, but there's a thing called quantum field theory, which is, without doubt, our best, most scientific explanation of the universe. So what is really going on is best described in quantum field theory, where everything is a wave. There's no such thing as matter. Matter is merely a wave, very condensed at a specific location. But yeah, it's weird, and until you actually, before you look at a subatomic particle, before you observe it, before you measure it, it is literally got a probability of being everywhere in the universe. It is part of a wave, rather like the, and this is not new to us, it's like the electromagnetism. We know that if we go to Pluto and we get two magnets together, they will attract and repel like magnets on Earth. There is a field, a fundamental field that is universal, and there's also a quantum field. And we touch on things like that in the course, believe it or not. Kids get this, let me tell you, they don't even, well, they find it weird, it is weird, but they don't question it. When I talk to my granddaughter, she sort of just accepts it and says, oh, yeah, okay. And, you know, the greatest scientists in the world accept it. And then we do exercises and games and all of that throughout the course. Now, I have done it, when I'm explaining something like superposition, it has no equivalence in the classical world. So it's very difficult to teach. So I tell stories which aren't 1000% accurate. That sounds bad. But they allow someone to understand what is actually happening. And even better than that, how calculations can be made. And I talk about that a little bit later. But I use my own, I've created this, I've not seen anybody else do this. I basically do a quantum Earth and a classical Earth. And then you can relate that to a switch. So on the classical Earth, which is in the top right-hand corner, we can only have, and I use A4 sheets of paper. So I say to the student, get an A4 sheet of paper, write 1 or 0 on it, and take the one with 0, go all the way to the North Pole and plonk it on the North Pole, and do the same thing with the South Pole. Now, that's all you can do in the classical world. However, in the quantum world, because of superposition, you can have A4 sheets everywhere. And then these A4 sheets get bigger as they near the equator. I show how we can adapt them and follow a trail to do computations, which is what happens. And then the beauty of it is, we can take the quantum Earth here, and entangle it with another quantum Earth, which you can't do in the classical Earth. So not only do you have millions and millions and millions and millions and millions of A4 sheets on one Earth, you can dynamically link them with a million A4 sheets on another Earth, and then that's called multi-dimensional Hilbert space. So I start bringing in technical terms, but one has to do it through story. And then with every chapter I put on further material, mostly YouTube. Isn't it wonderful that today I sit in regularly on MIT, Stanford University, Harvard, Cambridge, Oxford. They all broadcast their lectures now. It really is unbelievable. So I'm sitting there watching on my computer screen exactly what a student is listening to a completely #1 expert in the world. So, and most of this is on the net, so I do all the hard work and get them for you. And I've watched every single video that's on these links to make sure that they're suitable. The guy on the right is Dr. I forget now, Dr. Quantum or something, and he explains quantum entanglement and superposition beautifully in a fun way. I then, for every single chapter, oh, by the way, I should have said there were 6 chapters, and each chapter we do over 2 weeks. So the first week I do most of the talking, I guess. I get all the concepts over and we nut it out. And then the second one is we really deep dive into it. And after that, you will know the topic. It's great. But there's a quiz, a fun quiz at the end of every chapter. In this example here, and it's all timed as you can see, 30-minute quiz, so that's a bit over the top. But they're normally only about 10-15 minutes. And yeah, it's a fun way of doing it. In this case, I'm talking about exponential processing being so much different than linear processing. Every single computer in the world, not counting quantum computers, they process linearly. They may give the impression that they're doing it exponentially, but they're not. A quantum computer, because of the quantum Earth I was just showing you, and because of the multi-dimensional Hilbert space, it can do huge exponential processing. And I always say here, and try and answer this yourselves, guys. We're going to do the quiz already without doing the course. That's hard. If there are 8 people at a table, how many different place settings can you have at the table? So I could sit opposite Natalie. She could sit on my left. She could sit on my right, and all of that. With only 8 people, the answer is 40,320. And to show you how quickly it goes up, if you have 10 people, and this is a great quiz question to ask anybody, if you have 10 people at that table, the answer is C, 3.6 million different settings. For people out there who know, it's the factorial of 8 and the factorial of 10. But it's wonderful, and these are the things children love. There's young students up to 15 love this sort of stuff. And this is something you can put on the presentation. And then I find it very important that when young students present to, let's just say they may have 10 or you have a family gathering, their confidence just grows and grows. And I always say, if you want to learn a subject, lecture in it, because you will have to cover all the bases. Now, the course content, wow, I don't know whether I'm proud of it or not, because it's so extensive and challenging, but I guarantee at the end of this course, the young student will be streets ahead in this exceptionally important subject. So, I have 6 sections, 6 chapters. I'll quickly read them. An introduction to quantum physics. You have to have that. I talk to many people throughout the world who are experts in quantum computing, but they don't know the underlying physics. I'm alarmed how often I hear that. Don't worry about not understanding this, but in quantum computing, if you measure the qubit, it collapses to 0 or 1. Every single quantum computing programmer, code maker, applications developer, everyone knows that. I quite often ask them, do you know why that is? Oh, I don't know. No, I don't. And it's all down to this unbelievable experiment called the double slit. And I go through that. Well, I'll tell you about each chapter in a second, but you will understand exactly, because I labour the point, why it collapses to 0 or 1. And then an introduction to quantum computing, of course, what it can do and things like that. Third week is how do they work, because another thing to remember and to tell people and to quiz people, quantum computers do all of their quantum computations on subatomic particles, something a billion times smaller than a speck of dust. All of the computations is done at that level. It's amazing. It's just unbelievable. So as regards a real computer, they have actual, oh, I shouldn't say real computers, should I? That was a Freudian slip. As regards a digital fastest computer on Earth today, every digital computer has a transistor, basically, which can, so you put voltage through it, it's either on, it's either in there or it isn't, it's either 1 or 0, and that's the best it can do. But these subatomic particles are everywhere in the universe. And we can write to where these, it's called interference, where the superposition positively coheres, positive coherence, constructive coherence. We can reference that as well as any digital computer can reference 1 or 0. Unbelievable. And then I go through, as I was saying to Albert earlier, section 4, chapter 4, is about the quantum computing. So I actually show you quantum gates and quantum algorithms. A gate is something very simple. All gets down to linear algebra, which I explained to you as well. I'll talk about that in a second. And it's just basically one matrix multiplies against another. It's like a 1 A4 sheet. The calculation on one A4 sheet times another A4 sheet sends it to a different A4 sheet nearer the equator. I'll explain all that later. And an algorithm is just a collection of gates. Section 5, believe it or not, I will register you all and I will get you all to program a real quantum computer costing millions and millions of dollars from IBM. There's many of them now. When I was first involved in this, I was already involved, but in 2016, I think IBM put it's called the IBM Q experience, where they put the quantum cloud, where they have quantum computers throughout the world, in Melbourne, in the UK, in America, India, and they allow you to use them and do real calculations on them. I actually, in section 4, with the quantum gates, I show you how to put a qubit into a superposition. It's only 2 gates. But you can actually do that on the IBM real quantum computer, and you can really see it working and what it means. It really is fantastic. And many companies are doing it now, Microsoft, INQ, la-di-da-di-da. Section 6 is all about the different technologies. And this is what I mean when I say you'll know more than anyone else. Because at the moment, you see, with the digital computer, they all work the same way. Simple. They have an integrated circuit, heaps of transistors. They all work the same way. You may have a different metal, and silicon, of course, is what we all use, but la-di-da-di-da, it's all the same. Not so in the quantum computing world, because any subatomic particle, not any and every subatomic particle can be used. So you can actually do, and the Chinese did this just a couple of months ago, an incredible computation that would take the fastest computer on Earth half the time of the solar system, of the evolution of the solar system. So we're talking about 2.4 billion years it would take the fastest computer on Earth. They did it in 200 seconds. It's done a thing called Gaussian boson sampling. I might add it's a meaningless calculation, but that's not the point. That's a bit like saying when the Wright brothers first flew, they only flew for 50 seconds, whatever it was. This is going to take over the world very shortly. But it can be done on particles of light. It can be done on ions, thing called trapped ions, cold atoms, topological qubits that are their own antimatter. And I go into that a bit on a thing called the Majorana fermion, which is exceptionally exciting. And of course, superconducting, which is the main one. Superconducting, the qubit, the subatomic particle, has to be cooled down to just more than freezing point. Another question you can ask the world, what's the coldest place in the universe? And it's not somewhere billions and billions and billions of miles away from the sun, from a sun. It's actually at the bottom of superconducting quantum computing. But, 4 years ago, they were all like that. Now we have many quantum computers that work at room temperature. So, and quantum technology is already in your phone. So there's many things there. So they're the 6 chapters, and within those chapters, so if you remember, the first one was an intro to quantum physics. So for the first 2 lectures, I talk about what is quantum physics, what's superposition, what's entanglement, what's tunneling. Tunneling is basically where you can walk through walls, and then I give you links. This is exciting, and that program in America, which I've never ever watched, The Big Bang Theory, has really helped, because in The Big Bang Theory, they talk about entanglement, Schrodinger's cat, superpositioning, and quantum tunneling. But all quantum computer is, a guy called Richard Feynman in the mid-80s, he said, hold on, we don't understand this stuff. We don't understand superposition, entanglement, tunneling. We still don't understand it. After 100 years, we are a lot further down the line, but we still don't understand it. But the thing is, we can harness this power to produce quantum computers. So what is a quantum computer? I go into the qubit, how a subatomic particle is not in any place in the world, or the universe. It is a little bit in everywhere. There's more a probability than it's here than there, but it follows what's called a probability wave function. And we can follow that over time using a thing called the Schrodinger equation, which we don't get into in this course. We don't go into advanced maths in this course, but we do a fair bit of linear algebra, which in fact, so I talk about how quantum particles do mathematics, and it all gets down to matrix algebra. So you start off with it as it's normally initialized to 0, and then we can multiply it by a gate, and all that gate is a matrix. So you've got one matrix to start off, you've got an operational matrix, and then you multiply them together, and then you have a new matrix. And I explain that using A4 pieces of paper that keep getting bigger and bigger. I talk about linear algebra. Yeah, I'm almost finished. We're talking about linear algebra. You know what a matrix is and how you can multiply them together. I talk about what is a qubit and how multiple qubits work together by being entangled. And then the most important thing is the Bloch sphere. And the Bloch sphere is the analogy, is that quantum earth I was talking about before. And again, you can have questions and answers. I then talk about a gate, which is merely a matrix, and then an algorithm, which is a combination of gates. And then you've got more things to learn. I then take you through, as I said before, the IBM Q experience. And then I talk about the different technologies. And then there was a question before by Ty, what achievements has quantum computing made so far? Quantum computing has actually made a computation quicker than the fastest digital computer on Earth. It's called quantum supremacy. There's a bit of to and froing, but basically that's where it's at. So it's still very much setting the groundwork. The problem we have with quantum computers is that because they're on a subatomic particle, they interfere with the environment. So to keep them accurate, we have to counter a thing called noise. What are they going to do in the future? Well, they're going to do amazing simulations, amazing optimizations, things like and teleportation. So we will be moving things around the universe instantly. You know, there's caveats on that, of course, which I have to explain. I'm a bit of an expert on quantum teleportation. I've done presentations around the world on it to universities. So here's the link to the school. I might add, I did a presentation about 6 months ago to the Australian Computer Society, and they had the largest audience that they've ever had. It's about 630 people on Zoom. And they identified quantum computing as the most important thing that they wanted to learn. So look, that's the presentation. Can I have you back, Natalie?
Yep, I'm here.
Excellente. I can't see you at the moment, but not that matters. Oh yeah, put in the link. This is yeah. Thank you, Natalie. I'll pass over to you now, Natalie. You can maybe ask for questions or whatever you wish.
Right. Yep. So if anyone has any questions, feel free to unmute yourself. We'll just take a couple of minutes to do that.
Do you have a question, Natalie? Let's put you on the spot.
So there's a lot of terms in there that I'm sure you'd explain in detail during the course, especially for these children who are complete beginners to quantum physics and probably don't even know what a particle or an atom is. So basically, quantum computers are made up of these small quantum particles that are just extremely quick at what they do compared to a normal classical computer. Is that an overview of it?
Yes, that's essentially it, actually. It's just that because a quantum subatomic particle has this thing called superposition, and it's a good point you say about the jargon, like in anything, you have to explain the jargon time and time again. And the difference here is that superposition, we're not used to. It doesn't exist in the classical world. I can't be here and I can't be in the UK as well. But in superposition you can. And there's a thing called non-locality. It's like I could tap you on the shoulder. I have to be next to you. But that's not the way the universe works. The universe works that I can tap you on the shoulder. Even if I was a subatomic particle, I could tap you on the shoulder even though you're in the UK. It's like having an arm in Russia and a foot in China.
Well, if not, Eamonn, I want to thank you for coming on and hosting today. The course
Pleasure.
doesn't start until a month from now. Anybody is welcome to book now, or they can decide later on. Um, and it'll be once a week at an hour and a half per week. You have 2 days available, 2 session times, and it lasts 3 months. And then after that, if we have enough interest, we will offer the quantum teleportation first, and then quantum consciousness to just complete the package of 3 different subjects, really. So we hope that you will join us. And I guess that's all, Eamonn.
I'd like to thank you as well, Natalie. That's fantastic. Look, you're bringing my favourite topic here. Quantum teleportation at the moment can only be teleported spatially, so that's a distance, and you also have to send a classical bit as well. So, even though technically we could do it over billions and billions of miles, in point of fact, we can only do it where we can classically, so that's through anything within the speed of light, fiber optic, or even using the telephone, because we just have to. Now, you're bringing in time. There's a thing called temporal quantum entanglement, and there's a wonderful experiment which I do touch on, and this is something we might do a deep dive in. It's called the delayed choice quantum eraser experiment. And by using entangled particles, it actually proves that things that have already happened can be altered. So, yes, technically, we will be able to send things over time. And that means things like we could do the encryption code on atoms that don't even exist yet. So that's where we're at. This is weird stuff.
Perfect. Thanks, Eamonn. We will let them go now. And thank you, everybody, for coming along.